Edexcel Core Pure, second order differential equations 1, the homogeneous case. Auxiliary equation with repeated roots. We've already seen that when we take a second order linear homogeneous equation like this, that the auxiliary equation can have two distinct real roots. And that would mean that the discriminant was positive, b squared minus 4ac would need to be greater than 0, and the general solution would have the form y equals a e to the lambda 1x plus b e to the lambda 2x. So that's one possible scenario where the discriminant is positive. However, when we get to the auxiliary equation, it could be that we have coincident real roots or a repeated real root, for example m equals lambda. So this would give a complementary function of the form y equals a e to the lambda x. So that's one possible form of the complementary function. However, since the differential equation is second order, we know that we need two arbitrary constants. And it can be shown that by using y equals bx e to the lambda x, that would also be a valid solution to the original second order differential equation. So to get our general solution in this case, containing two arbitrary constants, we need a plus bx times e to the lambda x. Notice we've pulled out e to the lambda x as a common factor. So it contains both arbitrary constants, and it is the general solution when the auxiliary equation has a repeated real root. Something else that you could try and do is to take this solution for y, differentiate it, and sub it back into the original differential equation to verify that it is a solution to the original second order equation. So here we're finding the general solution to this second order linear homogeneous equation, and we're trying y equals a e to the mx, and my auxiliary equation, my ae, would be m squared minus 6m plus 9 is 0, which is a perfect square. It's m minus 3 squared, and therefore m equals 3, and there is your repeated real root at m equals 3. So to get to the general solution, we know we need two arbitrary constants, so you've got to remember that a plus bx, it's the plus bx, it's the extra bit that you need to remember. E to the 3x is a perfectly valid general solution to the original differential equation, and notice the two arbitrary constants a and b. So here the auxiliary equation, which we always need to be considering, had a single repeated root, which led to the fairly obvious a e to the 3x, but you also need to include the bx e to the 3x case as well in your general solution. And we can have a look at the solution in a little bit more detail using a Geogebra file. So at the moment I've set the two constants to equal 1, and so we're looking at the solution y equals 1 plus 1x e to the 3x, and when x is 0 we get a y-intercept at 1, which is the a value. So if I change a, we can see we're changing the y-intercept. And other things to notice: when x is positive, e to the 3x increases exponentially, so when x is getting bigger, y is exponentially getting bigger. And when x is negative, e to the 3x will decay towards 0. So there's asymptotic behaviour along this negative x-axis. So we've seen that the y-intercept equals a, and as x tends to infinity, y would tend to infinity. But if we start to change a and b, we can see different things happening. So if I go down to a is minus 1, for example, we can see the x-intercept is at 1. And by changing the a and the b, I can get a different x-intercept. For example, if I stop at a is 1, b is minus 2, the x-intercept is at half. Indeed, the x-intercept will be at a point called x equals minus a over b. So there will be an x-intercept when y equals 0, and therefore this factor would equal 0 when x equals minus a over b. So by controlling a and b, we can determine where that x-intercept might fall. So in the next video, we're going to be looking at auxiliary equation with imaginary roots.